Let's talk about image sharpening today. Before that, let's have a look at what we've seen in the previous video. We're talking about low pass filtering, also called smoothing. It causes a smoothing action on the image, on the input image. We've seen that this is obtained by replacing the pixel in the middle of the kernel by the average values of the neighborhood. We've seen this box kernel and this Gaussian kernel. Now, what it's doing, what's average doing? Average is doing a sum, right? It's summing up the it's the product of this value with the pixel that's right underneath it in the moving window, right? So you're moving this window around and you're multiplying each one of these and then summing them all up. What's this process of sum? This is an integration, right? So we obtain smoothing by integrating the pixels given the neighborhood. What do you think is going to be sharpening like? If smoothing is integration, sharpening is derivation, right? So sharpening or high pass filters, we're going to be talking, you hear both terms, either sharpening an image or passing or doing a high pass filter, spatial in the spatial domain. And sharpening is used to highlight transitions in intensity. Applications you can imagine: image printing, medical imaging, if you want to highlight a particular lesion in the medical image, industrial inspection to find defects, autonomous driving if you want to find the lane markings, or if you want to find the road signs, you use sharpening for that as one step of that. So as I said in the previous slide, if blurring is obtained by integration, sharpening is obtained by derivation. And the sharpening will be obtained as a response to the derivative operator. And the response of the derivative operator is going to be proportional to the magnitude of the discontinuity at that point. Now, the only thing we know how to do is what? Convolution, given kernels. The whole thing that we're going to be doing in this lecture today is convolution using sharpening kernels. And these sharpening kernels are obtained by means of derivatives. That's all what there is. Now let's see the maths. All right. So by enhancing the magnitude of the discontinuity at the points, it's used to enhance the edges and other discontinuities, including noise. So you're also enhancing noise. And de-emphasizes area with low varying intensities. This is a high pass, meaning that high frequencies are passed, whereas low frequencies are attenuated. And this is our well-known first derivative on one coordinate, and this is the second derivative on the same coordinate. This can be approximated by, it's just, well, a derivative is just a difference, right? Whereas an integration is just a sum. A derivative is a subtraction. So we are subtraction one step from fx plus delta x. This is the step of the derivative minus the value of the point at x divided by the step of the derivative. Considering that we have a digital image and we want to do, usually what we want to do is a step of 1 pixel. So we want to see what's the difference of this pixel with respect to this other pixel. Delta x is 1. So the first derivative becomes this very simple subtraction that is transformed into a kernel by this very nice matrix, right? So you see this is 1 times the pixel, the next pixel, that's pixel x plus 1, that's the positive 1 here, minus 1, the pixel before that, minus 1. And that's it. You have your first order derivative kernel. If I want a second derivative, and I'll let you do the proper mathematical derivation from coming from this to that. It's very easy. You just apply this formula twice. Let me clean this slide. We apply this formula twice to get into this. This is the format, an approximation of the second derivative on one dimension, which f, the value of the function at pixel x plus 1 plus the value of the function at the pixel x minus 1 minus 2 the value of the function in the middle. This becomes this kernel. This is the kernel for the second derivatives. Whereas this 1 times fx becomes this 1. This 1 becomes this 1. Whereas minus 2 is this guy in the middle. Right, people? That's all that. So why do we use this? This is a great way of analyzing changes. Well, the derivative, you analyze changes. A derivative is just a difference, and the difference, a subtraction, is actually how this number is different from the other number. So given an image, let's just pick up an horizontal section of this image, like what we had at the beginning. So if we have a two-dimensional image here, what we are seeing is a cross-section of that, and that becomes this intensity map here. Now let's look at this intensity map. This is a region of constant intensity up to a certain point in this cross section, and then there is a ramp. There is an intensity transition at this point, and a ramp down where the image that's very bright here becomes very dark, going down to another point where there is another change, and then the intensity becomes constant. And then there is another change. This is an abrupt change. It changes up and then it changes again. Now, if we look at the derivatives, let's see what the derivatives tell us about these changes. These are the values of the line. So it starts at 6, 6, 6, 6, 6, 6, 6, 6, then changes to 5, 4, 3, that's 5, 4, 3, 2. These are the values of the on the scan line. The first derivative is just the difference, this minus this. 0, 0. What is it representing? It's representing that it's constant. There is no change. There is no change here up to here. And the change occurs here when the subtraction is 5 minus 6. Then we know that at this point there is a change in intensity, right? This is minus 1. And this change in intensity becomes the same change from pixel to pixel. I'm not varying the intensities abrupt in weird ways like that. I'm changing them linearly, right? Changing them linearly. This is shown in the first derivative by keeping the same rate of change, the same rate of difference. Then it changes again. You see that the value changed. It became constant again. Became constant again, like at the beginning. And here it changes. The abrupt change is shown by a single number. So it's changed up, and then it's changed to constant again in the next step. Now, how do I pick up these are rapid changes? What's the difference between a constant change and a very fast change like this one? We look at the second derivative. Well, the second derivative is telling here there is a change, and then it became constant. The change became constant. Then there is another change, but that's a positive change. So it's changed to the negative, so we are losing intensity, if you're talking about pixels intensity. And then it changed again to, was a positive change. And then it became 0. And this kind of abrupt change, very fast change, is related to what is called a zero crossing that happens here, where the second derivative is positive and then becomes negative again. When you see that there is a very fast change, with very instantaneous change from one point to another point, and then it becomes constant again, as you see in the first and second derivatives, right? So they basically show everything that's going on in terms of changes in the intensities in a given image. Right. So one important second order filter that we've heard about many times is the Laplacian. And the Laplacian is just, again, I'll let you do the mathematical derivation yourselves. The Laplacian comes from, let me get rid of this. The Laplacian comes from this applied into the x and y coordinates, or z and w, depending on how many coordinates you have on your image. You can have a multidimensional image, right? So this would be fx plus 1, y plus x, fx minus 1 and y, and then it's the same thing on y. And the two-dimensional Laplacian, sorry, here there's a mistake. Should be y here, right? There may be a mistake in the book. Because there is a change, second derivative on x and a second derivative on y, and it's just twice this kernel here, right? But then this kernel is representing the x coordinate, and then I should have another component on the y coordinate of the exact same kernel, and becomes this kernel here. This is the Laplacian. This is the second derivative for image sharpening, a very important operator, the Laplacian operator. So the idea is to construct filter kernels from discrete formulations of the Laplacian kernels and apply convolution, as we've seen in the previous video. If you didn't understand convolution yet, go back to the video, read the book, search for places in the internet. On my very first lecture, I gave you some pointers. I'm going to put these pointers on our flow page. It's important that don't take me for granted. Look for more information outside. Right. So there is a number of Laplacian kernels. We've just seen the derivation, we didn't derive, but we described this kernel, which is the most basic Laplacian kernel. We could have this one with a -8 in the middle. We could have the same one, but this multiplied by -1. We end up with this kernel, and the same thing for this one. These are all Laplacian kernels. Let's see an application of them. Now, this is figure A, is a blurred image of the north pole of the moon. Right, it's blurred. And then I apply the Laplacian. This is the Laplacian image. This is the Laplacian image. Applying the kernel on figure 3.45a. Applying this kernel, right? This kernel. Okay, right. Let's look at the Laplacian again. Right, you see that the Laplacian enhanced, but what it carries is all of the abrupt changes. So it has all of the edges of the changes of intensities in the moon. So what do you do with this then? Well, you can simply add. You get your original image represented by f, x, y, and add the edges, given a certain constant here. Now, by adding the edge, let me get rid of these markings. By adding this Laplacian here to the blurred image here, I end up with this very nice, sharper sharpened image of the moon. If you look closely, you're going to see that the edges here are quite well pronounced, and I can see much better. It's a much better view of the craters, of the moon craters. Now, if I use this other kernel on figure 3.45b, 3.45b, what is it doing? It is intensifying the discontinuities, right? As it does that, and we do the same process, apply the Laplacian on this image, get a more pronounced Laplacian, which is not this, and then sum this image with this image and end up with this very nice, very sharp version of the moon. You can see that it's much more pronounced. Look at these craters compared with that, and this with that. Quite nice, isn't it? Now, yeah, so this is just a larger version, a negativized version of this one. You can see that. Right. So we've seen the use of the Laplacian with the second derivative. We haven't talked much about the gradient. The gradient is another very good, very important operator in image processing in computer vision. The gradient gives the direction of maximal change. We use the magnitude of the gradient, given how much it's changing. So basically, we use the magnitude of the gradient and try to move in the image. Well, if not you, but your algorithm moves in parallel to the gradient. That gives you the highest jump. So you see that the gradient point is orthogonal to the highest change, which is a boundary here. So if we always walk orthogonal to the gradient, what we are doing in the image, we are following the sharpest edges, the most pronounced changes. This is the main use of the gradient. Now, I've just said that I didn't need to draw. If you move perpendicular, that's the lowest jump, that's the border, that's the level. It's also called level sets. Two possible approximations for this. You can approximate the gradient using this formula or this formula, and depending on the definition of gradient that the magnitude of the gradient that you're using, either this as the magnitude of the gradient or this, you have different kernels, right? So and the kernels are just various distinct discretizations. Gradient kernels are just distinct discretizations for the gradients, for the gradient operator. Now, these are a few of them. These are very simple gradients called Robert cross gradient operators, but very useful. These are the very famous Sobel operators. We've seen the application of Sobel operators in the previous video, right? When that website where we could play with the kernels. Try that again. We did the right Sobel, the left Sobel. This one is this is the top Sobel and the left Sobel. And if you read on pages 185 to 187, again, just 3 pages. Please read them. Read them for me. You're gonna understand how these kernels are obtained. So, and gradients are used for edge enhancements. For instance, this is an image of a contact lens, and this is the Sobel operator of the contact lens, and it's enhancing exactly any potential defect that this lens might have. So, for instance, here, for instance, there, you see there's a defect here, there's a defect there. It's kind of a bulge here. This is sort of a it's thinner, this part here. It's a kind of a not round enough. Okay, now we can use all of that for image enhancement, and that's the final bit of this of today's lecture. Imagine that we have an image of this is an example of an image of the whole body scan. This one, probably a CT scan, if I'm not mistaken. The book tells the story properly. We can apply the Laplacian, enhancing, getting all of the discontinuities in intensity changes. Then we can sharpen this image in the same way we've done with the moon, with the image of the moon. Sharpen the image, obtaining by adding A with B, by adding this image A with this image B, right? Then once we have we sharpen the image, we can apply the Sobel gradient. This is the Sobel gradient applied on the original image. This is the Sobel applied on A. Okay, we can get the Sobel image, this one, in smooth then with a 5x5 box filter, obtaining this image. We can do further manipulations with that, and you see that so this is masking the image formed by the product of B and E. So we are multiplying B and E to find a mask, which is just a frame for the image, and then we can use that to sharpen the image by adding A and F. So we get A, the original image, and just add with F image to get this. And the final result, we can use we can get this G image here and apply a power law transformation to get a pretty clear enhanced version of your original image. Again, that depends on what you want to do with the image. For me, for my untrained eyes, I'm not a surgeon, I'm not a medical doctor, I think this image here, G, has more information. It's clear, has more, the information here is clearer than H, although I don't see the tissues, right? Once I superimpose this with the original, I can see better, and used in after using a power law transformation that we've seen a couple of videos ago, couple of videos back, we can see the tissues and how the bones are centered in the tissues. Again, that depends on the use of the image and how you're going to apply. This is a pipeline of the bunch of operations that we've seen in the previous lectures, and you're all knowledgeable enough to do that in the exam and as an exercise, as a laboratory exercise. We're going to talk about it later on, and so far that finishes our chat about chapter 3. And the next videos we're going to get into other subjects. Thank you.